Okay, hello everybody. So welcome to our third lecture. As a reminder, yesterday we discussed the static detector. We saw that the static detector, when it starts in the ground state, despite being coupled to the Minkowski vacuum, can still become excited if the interaction is on for a finite time, right? So finite time is really important here. And we also saw that if the switching is sharp, there's a higher probability of excitation. Now, if we instead turn on and off this detector adiabatically, and just basically take the limit in which the detector is on forever, then the detector is not going to click. Okay? So today we're going to discuss basically the Unruh effect. And I mean, there are several different ways of covering the Unruh effect. In particular, there is one amazing reference, this reference here, that covers pretty much everything regarding Unruh effect, at least until the point that it was published. But nevertheless, my presentation here is going to be more loose, more intuitive. So I base some calculations on this reference here, and some of the concepts on Barrow and Davis, and also on the course by Sergei Sibriakov that is at Pearson, which I also cited on Monday. Now, if you want to have other check other presentations of the same effect, especially if you want something more rigorous, I'd highly recommend that you check that reference, and also Eduardo Martin Martinez's course on RQI that is on Pearson that I mentioned yesterday. Okay, so with this disclaimer, let's start. So in order to help me later today, I will start with computing what is the Weidmann function in 3 plus 1D massless field. Okay. Right, so now if we have, no, just as a reminder, we're still in Minkowski vacuum. So we saw the general form of this Weidmann function yesterday, right? But we're going to restrict ourselves to the massless case. So when we have massless case, then the omega k is just going to be norm of k. Remember that omega k is square root of k squared plus m squared. Okay. In general, right? So in here it's just going to be the norm of k. So let's do this computation. It's a little bit tedious, I guess, but let's just do it. I will skip some of the steps, otherwise you take forever. So the Weidmann function for massless case and n equals to 4. Um, so we had this integral over d3k, and then they have the prefactor, which was 2 norm of k, 2 pi cubed. And now we have e to the minus I k times t minus t prime plus I k scalar product with x minus x prime, right? So we can write this as, I'm gonna use spherical coordinates now. So I will change for spherical coordinates, and this is gonna give me this measure. Then I'm gonna write the part that does not depend on the angles, okay? And then the part that depends on the angles. I mean, on just theta actually, which is gonna be I, K, which I can write already as I norm of K, norm of X minus X prime, cosine of theta. And then on phi, we don't have any dependence, right? right? So then I can just integrate the phi part and get rid of it. So I can just plug this in here and simplify here a little bit. So I just have k and then 2 pi q square, I mean, and then just repeating this part. And now if I perform this integral over theta, what I'm gonna get is I norm of k, norm of x minus x prime. And then here I have a term that is ik x minus x prime minus the negative, the conjugate of it. So this is the term that I get. Okay. Now I'll just recombine those terms, just re-express the same thing. So I'll pull out this minus I here, and then the 8 pi square, okay? Then also take out the x minus x prime. And notice that this k cancels with this one, okay? And then we're gonna have the integral from 0 to infinity of dk times, just rewriting, minus I norm of k times t minus t prime plus x minus x prime. And then the other one is going to be minus I k t minus t prime plus x minus x prime norm, right? Now, one important fact about this is that it's not going to converge. So this does not converge unless we add some real negatives exponent, right? So without some real negative exponent. So what are we going to do? We're going to actually analytically continue this. So we're going to take t minus t prime to t minus t prime minus I epsilon. And this I epsilon is going to be some real positive number, okay? Very small. So we're going to take now the limit. Well, let me just copy this first part, minus I for 8 pi square x minus x prime. And then we're going to take this limit when epsilon goes to 0 from the right of the exponent, the integral from 0 to infinity of dk of the exponent or minus I. Now we're going to just add this minus I epsilon, right? T minus t prime minus I epsilon plus x minus x prime. Then just basically copying the line before, right? But now I'm just taking t minus t prime to t minus t prime minus epsilon. So that is this. I think I made some mistake here. Wait, there shouldn't be, this should be, one of them should be negative. Okay, this one should be negative, right? Yes. Yeah, I think this one should be negative. One of them has to be negative. Yeah, okay. So what we find if we do this computation here, now everything is going to converge, right? So we don't have a huge problem because since we have ik here and then with this minus I epsilon, I'll get just something that is minor epsilon times k. So when I take this k to infinity, this exponent, this real exponent is going to kill it. So we're going to converge. So if you do this calculation, what we're gonna see is that this is going to be the limit of epsilon going to 0 plus of minus 2 times I norm of x minus x prime times t minus t prime minus I epsilon square minus x prime square. And I can simplify this. That's just the limit when epsilon goes to 0 from the right of minus 1 over 4 pi square times 1 over t minus t prime minus I epsilon square minus x prime norm square. Okay, so this is the final result. I recommend that you guys redo this calculation at home later. And I mean, check if I didn't make any mistake. It seems like I got some confusion at some point, but also fill in the gaps so that you have the full computation for yourself. Okay. Uh, questions or comments at this point? All right. So a comment that I have to make is the following. This is a distribution. Okay. This is a distribution, which is also called a generalized function. So the way to understand it is basically when you're integrating it against some smooth test function. Okay, so it must be understood um, under integrals against smooth, compactly supported test functions. Okay, so basically integrating against this well-behaved test functions. That is the idea here. Now, um, let's see. So we're going to compute a specific case of a response of a detector for the thermal bath. Because if you think about, everybody keeps telling you that an accelerated detector in Minkowski vacuum is going to see a thermal bath, right? So I thought that you'd be maybe clarifying or at least illustrative to see what is the response of a static detector when it's seeing a thermal bath of Minkowski particles, okay? So let's just have a look into that. So now I want to compute, and I promise the calculation that I just did is going to show up at some point. That's why I did. So let's compute the static uh, detector in a thermal bath in Minkowski. Okay. Okay, so let's start with defining what would be the state of the field, right? What is this, the state for this thermal bath? So uh, the I would define the state of the field as e to the minus beta h. This h is the free Hamiltonian of the field, right? So over the partition function, okay? So the partition function is just given by the trace of this e to the minus beta h. Okay. And now, what is beta? Beta is what you probably imagine, the inverse temperature. Okay. And in this case, for the field, what I have for this Hamiltonian is going to be the integral over d3k omega k, the creation, and then the annihilation operator. So here, implicitly, I already assumed, let me just add this, that we are in 3 plus 1 dimensions, okay? So you can see that this tree comes from the fact that we are in 3 plus 1. Now, this Hamiltonian is actually the normal order Hamiltonian, so normal order Hamiltonian, which means that I subtracted the vacuum energy, which is infinity. But it doesn't matter, right? We're not interested in the vacuum energy, so it's common to use this normal order procedure. Now, one important comment here before we proceed is that, in fact, I'm kind of cheating here. Um, this is a cute definition for thermostates, which is a Gibbs definition of a thermostat. And it makes a lot of sense when you have finite systems. It makes sense as well, at least in some cases, when you have infinite dimensional case, as long as it's countable like infinitely, but countable infinite. Now in QFT we have uncountably many, right? It's uncountably infinite dimensions. So this doesn't really work. So my comment is that this Gibbs definition of the density matrix is just to be understood formally, okay? Um, and that is because in QFT, where we have uncountably many dimensions, because in QFT we cannot define this exponential in the trace. So in other words, this operator is not trace class. We cannot even define this trace. But nevertheless, if you do some more rigorous treatment, uh, you're just going to get the same answer. So we're going to stick with this. Just have this caveat in mind, okay? Um, so rigorous treatment would be using other conditions that are going to lead to the same Weidmann function, or if you put your QFT in a box and then take the limit, a very large box, and you're still gonna recover the same result. So let's try to compute first the 1-point function. Okay, so the 1-point function, as I introduced to you guys yesterday, is going to be rho of the state that I'm interested in, which is this rho phi, right? Times phi of x. Now for the case that I have here, as I just defined, this rho, what I can rewrite is as 1 over z. The z is z of beta. I'll just write z, okay, for convenience. Times the trace of what? Of e to the minus beta h times phi. I'm going to expand phi in terms of the Minkowski modes, okay? Minkowski vacuum modes. So I will write this as I've done a few times by now, plus the creation operator. All right. Okay, so we want to compute that. If you notice here, I'll have terms that depend on e to the minus beta h times this annihilation operator, and some other terms that are depend on the trace of e to the minus beta h times the creation operator, right? So I will try to find some auxiliary identity to help us find the result. So let's see. Let's try to find this auxiliary identity. Okay, so first of all, notice the following. If I have e to the minus beta h times the creation operator, so for now, let's stick with the creation operator. And I can write something very simple that I believe everybody's going to agree, which is going to be just this times minus beta h. Okay? Now I have this nice object here, and I will remind you that when I have e to the x times y times e to the minus x, there is some nice expression for that. And what it gives is n from 0 to infinity of 1 over n factorial times the nested commutator. So we're going to have x with x with x with x with x and y. And again, continue. And all the way. So here we have n times of these commutators, okay, of these nested commutators. And the definition is that the zeroth order term is simply y, okay? So let's try to compute a few of these terms here. So if you notice in this expression that I have here, what I have is that x should be minus beta h, right? So beta is just a scalar. So let's look into the commutator between h and AP dagger. Okay, so that would be the commutator between, I can just pull out the integral. So I have omega k. Remember that I wrote here what is the Hamiltonian, okay? So I'm just rewriting it here. And then I'm going to have some commutator between AK dagger, AK, right? With AP dagger. So now remember that property that we learned in undergrad of like how to distribute this product here in the commutators. And remember as well that the commutator between AK dagger and AP dagger is going to vanish anyways. So what I'm gonna get is integral over the 3k omega k, and then I'll pull out this AK, right, for AK dagger for the term that is not vanishing, times the commutator of AK, AP dagger, right? And so I can maybe write here, this is going to be D3k omega k, AK dagger, and then this delta, right? Delta 3 of k minus p. And therefore, what this gives is omega p AP dagger. All right. So notice that we took the commutator between h and AP dagger, and I got this omega p times some AP dagger again. And if you just do this process again several times, what you're gonna see is that the nth term, so if I do the h um, AP dagger. That's it, right? Maybe here. This being the nth order, so n times. What I'm gonna get is simply omega p to the power n times AP dagger. Okay. Okay, so let's write this result using the formula that I shared with you guys earlier. So what we have is that e to the minus beta h AP dagger. So I'm just copying whatever I had here is going to be equal to, now plugging in the formula to replace this first part. Then we have summation from n equals to 0 to infinity of 1 over n factorial. And then because what I selected out as x had this minus beta here, all the terms are going to have a minus beta to the power n, right? But also in each of these terms, I have omega p. So I'm always going to get a minus beta times omega p to the power n. And then for each of those terms, I also had in a AP dagger. And for now, I only copied this red part here, right? So I still need to copy the rest, which is literally just copying, okay? So what this results in, if you notice, I'll just have some exponential here, right? So I have e to the minus beta omega p times AP dagger times e to the minus beta h. Okay. Uh, yes. Okay. So this is the identity that I was looking after. And this is going to be important. So I'm just putting a box here because we're going to use, and sometimes I may refer to it as, I don't know, the pink identity. There's no meaning on pink here. It's just the one that I circled in, put in a pink box. Marcos, do you want to ask your question? I'm not sure if I understand.
Um, it's just about the commutators between the annihilation and creation
Mm-hmm.
operators. Why is not using when you have the product? I don't think why we don't use the Leibniz, some kind the Leibniz rule to open this product.
When we have, uh, okay, let me just try to, I will write here. So if I have A, B with C, the commutator of this is going to be the commutator of A and C times B plus A times commutator of B and C. Okay? But then I did use that. But what I meant here was the following, that, okay, maybe I can open it up. So this is true. And then, but in the case that we had here, it was AK dagger, AK with, sorry that I skipped one step. So if I just plug the same idea here, what I have is AK dagger with AP dagger times AK. But this one is going to vanish. So I already didn't even write that one, you know? So I just wrote the other one. So the other one would be AK dagger times AK with AP dagger. This is the only one that I wrote. Sorry if I was too fast. Yeah, but I hope now it's clear. Okay, so again, this identity is going to be important. We're going to use it a lot. So let's try to use it. So using this identity, what we're going to see is the following. So remember that at the end of the day, we want to compute those traces that have some product of e to the minus beta h times annihilation or creation. So let's get back to that. So I want to compute some trace of e to the minus beta h times the creation operator, for instance, okay? So this is going to be the trace of basically using the same identity that I just found. So this is going to be the trace of minus beta omega p, right? Times AP dagger times e to the minus beta h. And well, this is just a scalar. The first term is just a scalar, right? So I will pull it out and then say that this times the trace of AP dagger to the minus beta h. And because of the cyclicity of the trace, I can write this as minus beta omega p times the trace of e to the minus beta h times AP dagger. Okay, it was a bit squeezed in the end. Sorry. Let me see if I pull it a little bit. Okay, let me rewrite this. Okay, now hopefully it's more clear. So I can write this equation as the following: trace of e to the minus beta h times AP dagger times 1 minus e to the minus beta omega p. I'm actually getting this left-hand side most, like leftmost, yeah, term with the rightmost term. And I'm getting this, that this is equal to 0, right? But this is equal to 0 for any p, right? For any omega p. And then just as a reminder, we have the omega p has to be larger or equal to 0. But this is true for any p, so what we can conclude is that the trace itself is going to be 0. So the trace, this trace here, is going to vanish. Okay? Um, Now, in order to not compute the other term, I can just recall a property with you guys. So this property is that when I want to compute the trace of the Hermitian conjugate of A, that is just going to be taking the trace of A and then take the conjugate of this trace, okay? So now if I want to compute what is the trace of the e to the minus beta h times the annihilation this time, what I can do is rewrite this using cyclicity first as, yes, AP e to the minus beta h. And now I can write this as the trace of the e to the minus beta h AP dagger and everything dagger, which is going to be, as I said before, the trace of e to the minus beta h AP dagger, but then taking the complex conjugate of this number, which was 0. So this is going to be 0 as well. So just to recap, we're computing this 1-point function. So we saw that the trace of e to the minus beta h times annihilation operators vanish. And the trace of e to the minus beta h times the creation operator also vanishes. This means that the whole 1-point function is going to vanish, right? So in conclusion, the 1-point function is going to vanish. The 1-point function vanishes. Okay. Now let's compute the 2-point function, right? So the 2-point function, as I said before, we tend to abuse the language a little bit and say the thermal Weidman. So I think at first Weidman was a word reserved for the vacuum one, but we are used to abuse this notation, abuse this language. So I'm going to write define using the letter Weidman as well. So the thermal Weidman is going to be given by um, 1 over z, right, times the trace of e to the minus beta h. And now I have the 2-point function, right? So I have phi of x and then phi of x prime. Okay, so let's have a look into this. Um, what does this look like? This looks like e to the minus beta h. And then I'm just going to expand this phi again in terms of the modes. So d3k prime. And I'll have again this annihilation operator times uk of x plus the creation uk star of x times ak prime with uk prime x prime plus ak prime dagger uk prime star of x prime. Okay. So now what kind of terms do we have to look at? Terms that depend on the trace of minus beta h. And this time we're going to have either two annihilation operators, two creation operators, or a creation times annihilation and annihilation times creation, right? So these are the terms that we have to look at. So let's start with one of them. Let's look into the trace of minus beta h times, let's start with creation. AP dagger, AP prime dagger. Okay, so as I said, the pink identity is going to show up many times. So we already start with it here. Remember, we have that e to the minus beta h times the creation operator is going to pull out this term times a dagger times e to the minus beta h. So let's do this. We already know that this is going to be just a scalar factor, so I can say minus beta omega p, right? Times the trace of AP dagger e to the minus beta h, and then AP prime dagger, right? Now I'm going to just use cyclicity of the trace again. So this is going to be equal to minus beta omega p times the trace of e to the minus beta h, AP prime dagger this time, times AP dagger. Okay. And again, I'm going to use here the pink identity. So if I do that, I'm gonna get e to the minus beta times omega p plus omega p prime, okay, times the trace of AP prime dagger e to the minus beta h times AP dagger. And again, I'll just use cyclicity to write. This is the trace of e to the minus beta h, AP dagger, AP prime dagger. Okay, so similar to before, now we have some expression that the left-hand side here uh, matches this right-hand side, except for this overall factor, right? So we can rewrite this as the trace of e to the minus beta h times AP dagger times AP dagger prime times 1 minus e to the, maybe I'll give some more space here, e to the minus beta times omega p plus omega p prime. And that is going to vanish, right? And that vanishes for general p and p prime. And again, recall the omega p plus omega p prime has to be equal or greater than 0. So in conclusion, we have that the trace of e to the minus beta h, um, ap dagger, ap prime dagger vanishes. Okay, so exercise for you guys using this result. I want you guys to show um, that the trace when we have both of the terms are annihilation, show that the trace of e to the minus beta h times ap prime is going to be 0 as well. Okay? So question so far, we've done quite a lot of calculations. No, seems like you guys are following. Okay. So now we need to compute two more terms, right? So what would be this other terms that we need? The cross terms, right? So let's see. We have the trace of e to the minus beta h times, say, the creation first, and then the annihilation p prime here. Okay, so again, we're gonna use the pink identity. So this seems like minus beta omega p times the trace of ap dagger e to the minus beta h, right? Times ap prime. All right. Now, this is going to be e to the minus beta omega p. And now I'm going to use cyclicity as well. Yes, let's use cyclicity again to put to put this AP dagger to the end. So I'm gonna write e to the minus beta h times EP prime times a dagger p. Okay. And okay, so what I'm gonna do here is going to be, let's see. All right, e to the minus beta h times. I'm going to write this AP prime AP dagger here as the commutator between AP prime and AP dagger. Okay, and then add back what I removed, which is AP dagger, AP prime, right? All right, so this here is going to be some delta 3 between of p prime minus p, correct? And then what we get is to the minus beta omega p times this delta 3 of p prime minus p times the trace of e to the minus beta h. Do you guys remember what is trace of e to the minus beta h that I defined before? That is going to be z, right? That's the partition function. Okay. And then on top of that, you have plus the trace of e to the minus beta h times AP dagger. Wait, I lost some prime here. Okay. All right. Uh, yes, that's the term. So what we get here is e to the minus beta omega p times delta 3 of p prime minus p times that plus e to the minus beta omega p times this trace of e to the minus beta h AP dagger AP prime, which again, if you pay attention, this term that shows up here is going to be the same term that is showing up here. Okay, so I'm gonna write that the trace of e to the minus beta h AP dagger times AP prime times 1 minus e to the minus beta omega p, okay, is going to be equal to e to the minus beta omega p times this delta function times that. All right. And then in conclusion, what we find is that the trace of e to the minus beta h times AP dagger AP prime is going to be equal to this e to the minus beta omega p delta 3 of p prime minus p times that over 1 minus e to the minus beta omega p. Okay, is that fine? Did you guys follow? I'll just, to write in a nicer way, I'll just multiply everything by e to the power of beta omega p. So I get rid of this prefactor in the numerator. So I'll get this times e to the beta omega p minus 1. Okay, so here we see that there's a Planckian factor showing up, which makes sense, right? Because we're computing the Wyman function in a thermal bath. So we would expect some thermal factors. And now, okay, so we already computed the trace of the e to the minus beta h times creation, annihilation, annihilation. Now we have this creation, annihilation. We just missed the annihilation creation, right? And then we are good to go. Almost good to go. E to the minus beta h. So we need the annihilation times the creation, right? Okay, so this term is going to give me the trace. Um, I guess I'll start with doing, let me see. I think the best way would be to do the, I'll do the commutator first. Yes, I'll do the commutator. So AP with AP dagger prime, right? And then I have to add back this AP prime dagger and then AP. So if I open this up, again, similar to what I had before, so this is going to be a delta of P minus P prime, right? And this is going to give me, and the trace that I'm going to have is going to be Z again, right? So I have a delta 3 of P minus P prime times the Z. This is just the first term. And then for the second term, I'm going to have the trace of e to the minus beta h times AP dagger prime AP. But this is just what we just computed, right? We just have that this trace of h minus beta h times the creation on P, annihilation on P prime is going to be this. So the only difference between this and this one is that we have to swap the place of P and P prime, right? So what we have here, I can just write delta 3 of P minus P prime times that plus delta 3. Now, delta of P minus P prime and P prime minus P is the same, right? So I can just write as P minus P prime times that times e to the beta omega P minus 1, okay? So if you sum this two, we're going to simplify to e to the beta omega P times the delta of P minus P prime times the z times e to the beta omega P minus 1, okay? Okay, so we have computed a lot of things, and now with all of this, we are able to actually compute the thermal Weidman, right? So let's try to write this. So recall the let's maybe copy here, because that would be a little bit easier. Or maybe I'll go to the next page. So let's say, this is the definition of the thermal Weidman, right? And okay, let's just plug in the terms that we saw that are not gonna vanish, right? So this is going to be, let's say, maybe I'll write the 1 over z inside actually. So I'm gonna write trace of e to the minus beta h. Um, what if I write sorry guys, sometimes it's hard to not skip ahead too much, but not and making a way that you guys understand. So I'm gonna write maybe the integrals outside. So it's just gonna be easier. D3 of k, D3 of k prime. Okay. So and then inside, what I have here is uk of x times uk prime of x prime dagger, which comes from, so I have this term that comes from uk of x and uk star of x prime. So this term came with what? Came with 1 over z of the trace of ak, right? Oh, I forgot the e to the minus beta h of e to the minus beta h of ak times ak prime dagger, right? And now I have still another term, right? What is the other term that is not going to vanish? Is this term here of creation with this annihilation. So for this term, what I have is uk star of x times uk prime of x prime times 1 over z. I'll probably write in the other line. Times 1 over z times the trace of e to the minus beta h times ak dagger and times ak prime. All right. So now, what do I have here? I'm going to rewrite, substitute what we found. So I have uk of x, uk prime star of x prime. And then if you go back, we want the annihilation times the creation, which is this result that we have here, right? This is the result. So that is going to be, let me copy. So this is the result that we have. And recall that we just divided by z. So the z is going to drop. And I have to plug in K instead of P here, and instead of K prime instead of P prime. So omega K, all right. Now the other term is going to be UK star of X, UK prime of X prime times, again, the Z that is here is going to cancel with the Z in the numerator. So what we have, let's see, for the creation and then annihilation. Creation and then annihilation was this. And again, we need to change P for K. And then get rid of Z. Okay. So now let's integrate over the K prime, let's say, right? So what we get is going to be the integral over K. So integrating over K prime, because of the deltas, we're going to see the K prime is going to turn into K. So we have, wait, UK of X, UK of X prime times the factor of e to the beta omega K times e to the beta omega K minus 1 plus UK star of X, UK of X prime times 1 over e to the beta omega K minus 1. Okay, so one could say, well, this is the final expression. And I think, yeah, this is a good expression. But we're going to go a little bit further. So let's recall the following. The expression for the Weidmann function. Okay, so we have the Weidmann function from Minkowski. It is given by the integral over d3k of uk of x, uk star of x prime, right? So what happens here is that if I manipulate this expression that I have here, I can pull out a Weidmann function. So I will write that this is equal to star, and then let's do the following. The star is going to be equal to the Weidmann part. So I'll have a Weidmann part here. And then what survives is the integral over of d3k times a factor of e to the, no, of 1 times e to the beta omega k minus 1 times uk of x, uk of x prime star here, plus the Hermitian conjugate. Okay, so this form of splitting is what we generally say is basically splitting the thermal Weidmann function into the vacuum contribution. So this part we discussed before, it's going to be divergent, right? Now, I mean, or you can understand it in terms of a distribution or generalized function. Now, this other part here is going to be a regular contribution. Okay, so that's the overall form that you can write it. And well, any questions so far? Okay, seems like no questions at this point. So now let's look into the specific case. that we are discussing, right? If you remember in the beginning of this whole calculation, it's been a while, what we wanted to compute is the case for a static detector in this thermal bath, okay? And so now what I want to do is, first of all, I will consider, let's consider the massless case, so massless field. Okay, so in this case, as I mentioned before, the omega k is going to be just k. And for static detector, then what we have is that t is going to be tau, and then the spatial part is just a constant. Okay, 0 or whatever. Okay, so in this specific case, for this specific case, we're gonna have the thermal part. So I'll try to write some notation here so that you know that this is the massless case where n equals to 4. And it's going to depend on the proper time, right? The tau and tau prime. And so this is going to be the Minkowski part for the static case. Maybe let's write here static as well. Static. And for massless and n equals to 4, similar to the other one. So I'm just gonna plug my result, my trajectory into that Whiteman that we computed in the beginning of the lecture, and then compute this other part here along this trajectory, right? So let's just plug in the term. So we have that this is going to be d3k, and then we have a term here of 2k 2 pi cubed that comes from the modes. Then we have the Planckian form, the Planckian term. So this is going to be minus beta k here. No, plus beta k minus 1, exactly. And then here I'll get, when we plug in the trajectory, the static trajectory, we're going to get minus I k times tau minus tau prime. And for the spatial part, we don't have anything, right? It's going to vanish. So it's going to be this plus the Hermitian conjugate, right? And all right. So if we plug in, let's just have a look into what was this Weidmann function here in the very beginning of the lecture. So we had this expression here, right? So let's copy it. So we had this was expression, but then now we are computing along a static detector, right? So if we have the static detector, what is it is going to show? What is it going to be? Any guesses? Just plugging in this trajectory that we saw here. What is going to be the contribution from the vacuum? From the vacuum Weidmann? I know you guys know this. No guesses? You guys were participating a bit less today, I think. Okay. So, well, if you just plug in, we know that t is going to be tau, right? So we have tau here. We have tau prime here. And then the spatial part is just going to drop, right? Because x minus x prime is going to be 0. So we know that this is the form that we have, right? Does it make sense? So now if you were to compute the other part, what we're going to see is that, well, I guess the best way would be to use, well, I can give you maybe one more step here, which would be that if you were gonna change for spherical coordinates as well, as we did before, and then when you compute, you're gonna get some 8 pi times the integral between 0 and infinity of some dk times k times 2 over 2 pi cubed. And then we have the factor to the beta k minus 1. And from this term here with the Hermitian conjugate, what we have is the cosine of k times tau minus tau prime. And remember that I mentioned before that this part is going to be regular, right? So I would say the best way, at least for me, the best way to solve this would be use Mathematica's function that is called Fourier cosine transform. And then if you use that, you're going to get the answer right away. So what we get here is going to be first term that we already computed. So minus 1 over 4 pi square times this 1 times tau minus tau prime minus I epsilon square. And then if you compute this other term, what you're gonna get from Mathematica is going to be one terms that is 1 4 square 4 pi square times 1 over t minus t prime minus I, no, just this. I'm already jumping ahead. Um, times minus pi square times beta squared, and then hyperbolic cosecant square of pi times tau minus tau prime divided by beta. Okay. And now what I'm gonna do is just say, oh, this function here is well behaved. This whole part is regular, so I'm just gonna analytically continue that part as well. So I'm gonna write this as minus 1 over 4 pi squared times 1 times tau minus tau prime minus I epsilon square, and then plus the other term that is going to cancel this one, right? So tau minus tau prime minus I epsilon square, then minus pi square over beta square, hyperbolic cosecant square of pi times tau minus tau prime minus I epsilon over beta. Okay, so the result is going to be simply minus pi square over beta square. Wait, I think I forgot. Yeah, I think I forgot that there was some pi square multiplying before in the result from the integral. Okay, I think this is just 1. Yeah, this should be 1. This is 1 times cosecant square of pi tau minus tau prime minus I epsilon over beta. Yeah, I think I got confused because I forgot the prefactor coming from the mathematical Fourier cosine transform. Sorry. But then that should be correct. Let me see my notes. Oh, there's a fourth. So there was, sorry guys. Okay, there's a 4 here. So yes, so there should be some 4 beta square here. Yeah, now it should be right. It should be correct. Okay, so this is the final expression. Um, okay, so questions at this point. Now that I see that you wrote something in the in the chat I didn't see before. Do you want to ask the question again? Luis, do you want to open your mic and ask the question or maybe type? Um, okay. Sorry. Um, all right, sorry. So okay, so this is the result. So we computed the Weidman function for the case of the static detector in a thermal bath of Minkowski particles, okay? So now what we're gonna do is compute the Unruh effect, right? We're gonna see what this accelerated detector is gonna see when it's traveling in a Minkowski vacuum. All right, so let's do the Unruh effect. Okay, so now let's consider an accelerated detector. A Minkowski vacuum. Okay, so its trajectory is going to be given by T of tau is going to be 1 over A hyperbolic sine of A times the proper time. Now I'll choose one direction, for instance, that I'll call X. And in that direction, the trajectory will be 1 over A times cosine hyperbolic of A tau. And in the other directions, I'll just keep it at the same position. So I'll just say that it's going to be 0. Okay? So I just align the movement trajectory with one of the directions. Now, what I'm gonna, what this, the property that this has is that it has this trajectory constant acceleration A, okay? And I've also consider to be easier to compare with my other case that we have a massless field in 3 plus 1 dimensions, right? So again, I think I have said this a few times, but let's recall again. What is the Weidman function for massless field n equals 4? I think by the end of the lecture, you're gonna memorize this, I guess. It's going to be the limit of minus 1 over 4 pi square, right? Times 1 over t minus t prime minus I epsilon square minus norm of x minus x prime square. Okay, so we want to plug the trajectory here, right? So we want to compute what is the trajectory? What is this function along this trajectory? So let's see. Along the trajectory, um, we get, let's first see t minus t prime here, what it is. So this I can write as just 1 over a squared. So just remember what is t, right? So this is going to be 1 over a squared times sine h of alpha tau minus sine h of alpha tau prime, everything squared. And then for the spatial part, what I have is also 1 over a squared, right? But then this time we have cosh, right? It's cosh of alpha tau minus cosh of alpha of a tau prime, a not alpha. Okay, now let's use the following identities for caution sign. So we have the sine h hyperbolic sine of x minus hyperbolic sine of y can be written as 2 times the hyperbolic cosine of x plus y over 2 times um, hyperbolic sine of x minus y over 2. Okay, now for the other one uh, that we need is going to be hyperbolic cosine of x minus hyperbolic cosine of y, right? And that one gives you 2 sine h of the sum times sine h of the difference. All right? So basically, we're going to use those identities and plug them back into those expressions. Okay, so here I'm going to get that t minus t prime squared is going to be 4 over a squared. 4 over a squared times cosine hyperbolic squared of a times tau plus tau prime over 2. And then hyperbolic sine squared of a times tau minus tau prime over 2. Okay. And if we do the same for the x part, what we get is 4 over a squared times hyperbolic sine square of the sum a times tau plus tau prime over 2, and then times the sine hyperbolic sine square of the difference, right? So we can rewrite t minus t prime squared minus x prime square as 4 over a square. Now I'm gonna put the hyperbolic sine square of a times tau minus tau prime over 2. Uh, I'm gonna factor this out, right? So then I'll get a times tau minus tau prime over 2. And then here I just get cosh square of a tau plus tau prime over 2 minus sinh square of a times tau plus tau prime over 2, right? And then there is an identity that says that this is simply 1. Okay, so what I'm gonna get here is 4 over a square times simply this first term, right? Okay, so far so good. All right, now I guess it makes sense to discuss one little thing. Well, we saw this part here, right? But if you remember what I had in the denominator here had also this minus I epsilon, right? So let me just make this remark. So what I had is that t minus t prime minus I epsilon squared, and that part is simply t minus t prime squared minus 2I epsilon times t minus t prime minus epsilon squared. But that part doesn't really matter. I don't, it's higher order, okay? I don't really care. Now I can rewrite this minus 2I epsilon times t minus t prime as what? Just plug in what is t minus t prime. So remember that, well, t minus t prime I computed here. This is the square of it. But if you just look into the expression for sine minus sine of a tau minus sine of a tau prime, I'm gonna get this expression here, right? So what I have is minus 4I epsilon over a times this cosine of a times tau plus tau prime over 2 times the sine, hyperbolic sine of a times the difference. Okay, so this is what we will obtain. Whereas, let's see what would be if instead of having 4 over a squared times the square of the hyperbolic sine, evaluating this point, if I evaluate instead of tau minus tau prime, I put into tau minus tau prime minus I epsilon. So I want to understand what would be 4 over a squared times the square of a here times tau minus tau prime minus I epsilon here over 2. Okay, so if I expand this is going to be 4 over a squared, just the term without the epsilon, right? And then the other contribution is going to be 4 over a squared. The correction is going to be minus I epsilon over times a over 2. And then I have 2 hyperbolic sine of the difference times cosh, but cosh of the difference as well. Oh, okay. It's a bit ugly, but so if you notice, there's a small difference here. Well, let me just maybe simplify a little bit more. So this is going to be equal to just the first term. So I just have this original term that we computed. And then here I can rewrite as minus 4I epsilon over A times cosh of the difference times sine hyperbolic of the difference. Okay, so now if we compare this correction here with this other one, we're gonna see that there is a small difference, right? Because this cosh here comes with the sum, whereas this cosh here comes with the difference. That is basically the only difference. However, recall the cosh is always positive, so both of those are going to be positive, right? So cosh, no matter if it's this or the other one, they are always positive. So the strategy here is just to define some new epsilon, okay? So this new epsilon is just the old epsilon times one of the coshes um, divided by the other one. So here epsilon is just a parameter, right? Epsilon is just a positive number that I'm going to take to zero anyways. So I can redefine it as I please. That there is no huge problem on that. No difference. I'm taking the limit of it going to zero anyways. Okay. So if I do this calculation, this definition, then what I can see is that I can write this Weidman of the accelerated detector for massless case, and then for n equals to 4 as the limit of epsilon going to 0 from the right. And this epsilon is the other epsilon actually, but it doesn't matter. Of minus 1 over 4 pi squared times a squared over 4 cosh square of a times tau minus tau prime minus I epsilon, okay, over 2. Okay, so this is going to be the Weidman function for the accelerated detector in the Minkowski vacuum. So we want to compare this with the other one, right? So we want to compare this with the thermal Weidman, right? With the Weidman for the static detector in the thermal bath, which is what? Which we found for massless case and n equals to 4, u of tau, I forgot to write of tau and tau prime. We found that u was the limit of epsilon going to 0 of minus 1 over 4 beta square times cosh square of pi times tau minus tau prime minus I epsilon over beta, right? That's what we found before. So they look very similar, right? Don't they? Can't we match them somehow? Right, one in terms of the other to review somehow that this Weidman is the same as that if we define some of the constants as in terms of the others. So if you notice, if you pay attention for 1 minute, you're gonna see that if we make this beta equals to 2 pi over a, the two match. The two correlators match. Okay, so what we can conclude that the accelerated detector perceives a thermal bath um, at temperature T equals to, which is 1 over beta, right? Which is just going to be A over 2 pi. Okay? Now, I guess it'd be useful to restore the units here. So if we restore the units, um, we're gonna get that T is going to be H bar times A over 2 pi C KB. Okay? And this prefactor here is really tiny. Okay? So we must have a huge acceleration to be able to measure this effect. So we must have a huge A uh, in order to measure this effect. So that we have some perspective on that. What a nice example that I think everybody always says when they present Unruh effect. That's my impression. Is that to observe uh, the temperature of just 1 Kelvin, okay, we need uh, an acceleration of order of 10 to the 20 meters per second square. 10 to the 20, guys. So that means that it's really, really hard, very hard to experimentally observe. Okay. Um, any questions here? I think it's a nice place to ask questions, I guess. You guys are quiet today. Okay, you're asking questions. Let me see. I mean, the acceleration that we're discussing, that I mentioned here, I mean, we don't we don't know. Yeah, we cannot achieve this. Of course, no, we cannot achieve this. Uh, how much energy? Yeah, as long as I checked, it's just like billions of the maximum energy that we can do in some rock science. Um, yeah, that's as much as I checked, but it's basically impossible for us at this stage. That's as much as I know. Yeah, so it's just realistically we're not gonna measure this. But um but then I should have said some things like remember that I mentioned in the beginning of this lecture that I was going to be a bit more loose and intuitive, and there are several presentations of Unruh effect. Some are more rigorous, some less. But I guess one thing that I should say is that I was cheating a little bit. So let me write some comments here. So by cheating, what I mean is that I handpicked our examples. Okay. And what do I mean by that? It means that for illustration purposes, I wanted you guys to see this Weidmann function of the thermal bath to match the Weidmann function of the accelerated detector in Minkowski. So what I did was I picked a case in which they match, right? So I basically picked a case in which the two Weidmann functions match. Now, okay, I didn't do that to mislead you guys, but because I find beautiful to see that at least once, right? Just to be able to believe it a little bit more. Uh, However, if instead of the massless case, I picked the massive case, this wouldn't be true. So, um, had I picked a massive field, for example, this would not be true. This would not be true. In other words, if I compute the same examples that I computed for you guys, but use the massive case, just scalar field with mass, then they would not match. So we need some other, like basically a more general notion of thermality, right? So we need some more general notion of thermality. Okay, so to just discuss this briefly today, let me see. Well, let's go to the next page. So some basics about thermality. Well, there are some different notions of thermality. Um, One of them would be the one of Gibbs thermality. So Gibbs thermality would be when the equilibrium state is going to correspond to some maximization of the thermodynamical entropy, right? So the equilibrium state corresponds to a maximum of some thermodynamic entropy. And this maximization is doing under some constraints, right? Under relevant macroscopic constraints. For instance, fixed energy, right? Now, the one that I presented to you guys before, like that Gibbs state that I presented, was actually the maximization of the von Neumann entropy, which in general is not a thermodynamical entropy. It's a quantum information entropy, which if you don't remember is minus trace of rho log rho. That's the expression for this entropy. But nevertheless, it works in our situations. And remember that I mentioned as well that this notion of Gibbs thermality makes a lot of sense as long as we are not in situations of uncountably many dimensions, which is precisely the one for QFT. In order to generalize this notion of thermality, there are those so-called KMS conditions. And these KMS conditions, they are imposed on correlation functions. And I think there would be the most general notion of thermality. Uh, so they're more general than Gibbs thermality, and they are also valid in QFT. So they're a bit harder to state in terms of the math, but they are the most general notion of of thermality that you have. Thermality, here in the loose sense, I'd say, like when I can uh, say that I'm observing a thermal bath, let's say. How can I say that this is a thermal bath, or how can I say that this observer that is accelerating through Minkowski vacuum is actually thermalizing? How can I say that it's seeing a thermal bath? That's the meaning that um that's what I mean. I'm meaning in a very broad sense. Okay. Um Now, so as I said, there's this notion of Gibbs thermality, there's this notion of KMS conditions on correlation functions. If you guys want to know more about that, I think Eduardo's course teaches really well. Like it goes through it in maybe 3 lectures, so it's quite a lot of content, and it gets more complicated in terms of the math. But for our purposes, because we're talking about detectors, so for detectors, what makes sense is that if the detector is acting as a thermometer, right? So we're using this detector as a thermometer. So if I want this detector to behave like a thermometer, it should thermalize, right? So it should thermalize to the same temperature as the bath that it's in, right? Let me see, there's one question. Um, Yeah, so Marcos, what you asked, I think the notion that you're talking about would be the notion of Gibbs thermality, right? So this thermal state would be some stationary state, right? That maximizes this entropy, right? Some entropy that you're defining, right? Would be the meaning that makes sense for us in terms of stat mach, right? Now, what happens is that these KMS conditions, they are going to generalize in situations in which the notion of thermality that we have does not apply. So when we cannot actually define this Gibbs thermality, these KMS conditions are still well defined. And interestingly, also, whenever Gibbs thermality is well defined, it matches KMS. So KMS is really a generalization, you know? Um, But I guess maybe I can discuss a little bit more of that soon. Let me just finish quickly here. Let me try to see how the detector is going to tell me whether it has thermalized or not. Okay, so for in terms of the detectors, I want to consider that this UDW detector is acting like a thermometer, right? So in order to do that, it should thermalize. So what makes sense is that it thermalizes um, if in the long time limit it approaches a Gibbs state, okay? And just recall that for the UDW detectors, this Gibbs state is well defined. So what I'm gonna say is that if I turn on and off this detector in a very smooth way, so adiabatically way, and take the limit in which this detector is on forever, it should become a Gibbs state. Okay, so I'm gonna write that this is the limit of time going to infinity of this. final state of the detector after interacting with the field, it should approach this Gibbs state, okay? Times the trace of e to the minus beta ht. All right. Now, this is what the intuition would be, right? But what is actually used, it would be the so-called detailed balance condition. So what is usually used as a diagnose for thermalization is going to be the detailed balance condition. Let me write in another color. The detailed balance condition. Okay, and what does it say? It says that the limit of long times, the probability of excitation divided by the probability of the excitation is going to be equal to e to the minus beta omega. Okay, so I'll write this in words so that it's clear to you guys. So again, I'm just reinforcing the idea that we have to have a detector on forever and has to be adiabatically turned on and off so that at least when we put in the vacuum, as we did yesterday, the detector should not click. Okay, so and I want this limit of switching uh, the detector on and off adiabatically and keeping it on forever. Um, in that limit, the excitation to the excitation ratio is governed by this Boltzmann factor. Okay, that's what this detailed balance condition is saying. Okay, now if you think similar to me that well, for a detector to thermalize, it should actually be in a Gibbs state. Uh, you can see that the Gibbs state is going to satisfy this detailed balance condition, but it also satisfies something else. So the Gibbs state satisfies the detailed balance condition. Okay. Obviously, right? Because this is just talking about what is the relation between those diagonal terms. But it also has to satisfy something else, which uh, is that the coherence in the so the coherence term, so outside the diagonal, have to vanish, right? So I have to have vanishing coherences um, in the long time limit. And this is true for any initial state. So I can start, I don't need to start my detector in the ground state. I can start my detector in any initial state, and this still, and I would still be able to recover this Gibbs state. So to recover this Gibbs state, I will still have need this coherence to vanish in this long time limit. Okay, so requiring this the final state of the detector in this limit of being adiabatically turned on and off and just keep it on forever It's a bit more restrictive than this detailed balance condition, but you're gonna see in the literature that basically for detectors they are going to require this detailed balance condition. That's all they are going to require, which is simpler to prove as well. Okay, let me see. I'll just have a look into the questions. Yeah, I guess Pedro answered and in a very nice way. Thanks, Pedro. Um, all right, guys. This was pretty much what I had for today, but there's only one more thing that is a homework, quote unquote. I wanted you guys to just search, search a little bit, like maybe spend 5 minutes, at least something, just a little bit of time about the so-called circular Unruh effect. Okay, so at least have an idea of what it is, but maybe if you can, it would be nice to have some discussion tomorrow. If you come up with one pro and one con of is this Unruh effect? Is this also Unruh effect or not? Okay, you'd be very nice to start tomorrow with this discussion. That is pretty much it for today. Thank you so much.